All right, welcome back to the Explainer. Today, we're stepping into what feels a bit like a groundbreaking 1980s tech unveiling, but, for the absolute bleeding edge of modern operating system design. We're diving deep into the Sexos UI stack, and we are literally going to reveal the most advanced display variant ever built. We're talking about a genuine zero-latency UI revolution, and it's all powered by this holy trinity of architecture: SexDisplay, Silk Shell, and Linen. Okay, let's dive into this with a really profound quote from our source material that perfectly outlines the core problem we're facing today. It goes, Wayland assumes the GPU is interactive. Sexos replaces this. You see, traditional compositors like Wayland and X11, they operate under a fundamentally flawed assumption. They act like these blocked, queued up trains, right? They're constantly negotiating with client applications about when and exactly how to render pixels. They treat the GPU as an active participant in this chaotic, noisy conversation, and that inevitably leads to dropped frames and that annoying visual stutter we all hate. So legacy systems basically choke on these client-server buffer negotiations. They rely heavily on bloated compositors and blocking communication. But Swixos, it cures this by replacing that jammed-up queued train with a continuous river of state. Instead of all these programs arguing over who gets to draw next, it's just a pure, predictable flow. It uses a causal execution machine. That means zero negotiation, just a discrete, totally uncompromising projection of the current state. And the pipeline flow for this UI stack is beautifully simple, moving perfectly through a single address space. Here's how it works. Raw input events flow straight into Silk Shell. Silk Shell then translates that input for Linen to update the scene, and finally, SexDisplay steps in to commit that exact mathematical state right to your screen. Let's actually break down these three revolutionary components one by one because they are fascinating.
First up, we have Silk Shell. Now, this piece actually lifts some brilliant concepts from the best modern window managers out there. It takes the highly dynamic, scriptable tiling ideas you'd see in compositors like River and Hyperland, and it pairs them with the incredible extensibility of Lua. But here's the kicker. It rebuilds all of that power as a stateless reactor. Silk Shell doesn't draw a single pixel, not one. Its only job is to listen to raw hardware input events, execute the logic, and push snapshot handles of the user interface state.
And because Silk Shell is entirely stateless between frames, it brings this almost magical property to the operating system. It manages isolated execution capsules rather than those messy, tangled process trees. So what happens if Silk Shell crashes? Well, the kernel simply drops its tombstone and restarts the Silk Shell continuation in the very next epoch. Your display doesn't freeze up. Your screen doesn't just go black. The system just keeps flowing flawlessly like nothing happened.
Moving right along to the second pillar, we have Linen. Linen is defined as the causal graph. Think of it as a declarative scene graph that lives entirely inside shared memory. If Silk Shell is the behavior of the system, Linen is the structure. It's basically a master blueprint of your screen just hanging out in shared memory. And this brilliantly illustrates what Linen really is: pure mathematical state. It's a tree of objects, rectangles, text, textures, you name it, but it knows absolutely nothing about mouse clicks, and it completely separates the mathematical UI state from the actual physical rendering of the screen. It doesn't do anything active, it just exists, waiting to be read.
Now let's unveil the final piece of the Trinity, SexDisplay. This is the commit engine, or, if we're being formal, the display state reduction engine. SexDisplay is the absolute sole owner of the physical frame buffer, period. It is the ultimate authority on what actually lights up the pixels on your monitor. Unlike Wayland, SexDisplay doesn't do negotiations. It doesn't care what client applications want. It acts strictly as a deterministic state reducer, literally a pure math function. It just strictly samples the lining graph, resolves the z-order of the windows, and blits those pixels directly to the hardware display buffers using atomic commits. It is entirely 100% uncompromising. Which brings us to this mind-bending number, 2.77 milliseconds. That is the blisteringly fast V-blank sampling rate of SexDisplay when running on high-end hardware. To put that into perspective for you, that is fast enough to perfectly saturate a 360 Hz gaming monitor without even breaking a sweat. Every 2.77 milliseconds, SexDisplay wakes up, evaluates the entire state of the universe, and projects it. Boom, done. I absolutely love this analogy from the sources. The legacy pipeline is a train, waiting for cars to be loaded. But the SexOS pipeline is a continuous river of state.
SexDisplay simply dips a bucket into this river every 2.77 milliseconds. If an application hangs or crashes, who cares? The river keeps flowing and SexDisplay just scoops up the last known mathematical state. No stuttering, no freezing. Okay, so we've got this beautifully decoupled mathematical rendering system. But this raises a really crucial pivot question. How do we actually click on anything without a traditional window manager figuring out where our mouse is? Seriously, if Silk Shell is stateless and SexDisplay is just a math function, who actually handles the mouse click?
The answer to that is the hit lattice. It's an O1 spatial hash grid designed for instant hit testing. Instead of asking a window manager to go digging through a messy, overlapping pile of windows to figure out what you just clicked on, Saasos maps the spatial coordinates directly to node IDs right on a 2D grid. Think of it like a chessboard. It knows instantly what piece is on what square without having to search the whole board.
So the crucial point here is the staggering difference in latency. Legacy UIs have this frustrating latency floor because they rely on slow tree walking that just gets slower and slower the more complex your UI becomes. The hit lattice, on the other hand, gives you instant O of 1 resolution. It completely bypasses the desktop shell. Finding a click in a user interface with a million nodes is exactly as fast as finding a click in a UI with just one single node.
Now, to understand how all of this is physically possible without just grinding your CPU to a halt, we have to look at the overarching architecture, Saasos, or the Single Address Space Operating System. In Saasos, there are no heavy page table swaps, none. Silk, Shell, Linen, and SexDisplay all live right there in one global 64-bit memory map. And they're securely isolated not by slow software boundaries, but by lightning-fast Intel MPK hardware keys that act basically like VIP bouncers inside the CPU. Let's ground this dense computer science for a second with some absolutely jaw-dropping performance metrics. Look at this. Communication latency drops from 1,200 cycles in a standard Linux baseline down to just 340 cycles in Saasos. And the memory footprint? It plummets from over 12 megabytes down to less than 128 kilobytes. The entire system is fundamentally 96 times smaller and 3.5 times faster.
And how does it achieve that speed? Through what's called the zero-copy singularity. When Silk Shell creates a UI frame, it doesn't copy those pixels over to SexDisplay. No. Using a rapid WRPKRU hardware instruction, the kernel instantly passes the baton. It grants read access without copying a single byte of data. It is the absolute pinnacle of efficiency. Now, what's really interesting about this slide is the final result of all these radical architectural choices. From the exact moment your mouse sends an hardware interrupt to the moment SexDisplay samples the mutated UI, the total interactive latency is approximately 3.0 milliseconds. This proves, without a doubt, that this completely experimental operating system architecture isn't just theory anymore. It is incredibly viable for daily driving. And the roadmap for the future of SexOS is just wild. It's evolving from a blazing fast compositor into a formally verified computation substrate. The architecture essentially allows for zero downtime updates. Theoretically, you could induce a fault and hot swap the bare metal compositor on the fly. Imagine just swapping between a Hyperland-style layout and a River-style layout instantly, without the desktop ever crashing or restarting. So I'm going to leave you with this provocative thought. If your operating system operates as a perfectly deterministic mathematical river, where the UI is nothing more than a strict projection of pure state, does the legacy era of chaotic, stuttering, crashing software finally end today? Based on the architecture we've explored, it certainly makes a compelling case. Thanks so much for joining me on this explainer, and keep exploring the bleeding edge of tech.